Everyone, in this video we're looking at what is symmetric matrices, right? Symmetric, antisymmetric, and skew-symmetric. All right. Okay, so before we can determine whether a matrix is symmetric, antisymmetric, or skew-symmetric, we need to know what a transpose is. And if you've been watching the video so far, the transpose of a matrix A, which is given as A, B, C, D, is simply A to the power T, and the transpose, what it does is to change all our rows into columns and all our columns into rows. All right, so if I want to transpose matrix A, I pick either the row or the column. If I pick a row, then it means I am changing to a column, and if I pick a column, then it means I'm changing to a row. So if I pick the first row, AB becomes the column AB, and if I pick the row CD, it becomes a column CD. Alright, so it doesn't matter whether you're picking a column and changing to a row, or you're picking a row and changing to a column, the result is always the same. Alright, so that is how we transpose a matrix. Now, if I have a matrix, matrix A, alright, let me use a different name, matrix B, which is equal to 1, 2, 2, 5, then B transpose is equal to, I pick the row, the first row 1, 2 becomes column 1, 2. Pick the second row, 2, 5 becomes my column 2, 5. Now if you noticed, if you check these two matrices for B and B transpose, you notice that B is the same as B transpose, because the first entity is 1 and the first entity is also 1 in B transpose, the second is 2, the second is also 2. If we move on to the second row, the first entity is 2, the first entity in B transpose is also 2, and the second entity is 5, second entity in B transpose is 5. So B is the same as B transpose. If a matrix and its transpose are the same, then such a matrix is said to be a symmetric matrix. Symmetric matrix. All right. So another example, if I have matrix A as 1, 4, 6, 4, 2, 7, 6, 7, 3, if I find A transpose, this is gonna be, I pick the first row, becomes a column 1, 4, 6. Pick the second row, becomes a column 4, 2, 7. Pick the third row, becomes a column 6, 7, 3. Now if you look at A and A transpose, you notice that A is the same as A transpose, and this is because they have the same dimension and the components are the same and at the same position. All right, so since A is the same as A transpose, we say matrix A is symmetric. Okay, then let's look at another example. Let's say matrix C is equal to -6, 8, 12, 8 minus 4, 2. You have 12, 2, and 9. If I find C transpose, this is equal to, pick the first row, becomes a column, -6, 8, 12. Pick the second row, becomes a column, 8 minus 4, 2. Pick the third row, becomes a column, 12, 2, 9. Once again, C and C transpose are the same. Therefore, C is a symmetric matrix. All right. Now let's look at something here. If I have matrix A, okay, given as 1, 2, 3, 4, and I find A transpose, this is going to give me, I pick the first row, becomes my column 1, 2. pick the second row, becomes my column 3, 4. Now, although A and A transpose have the same dimension, but the components are not the same and at the same position, right? Although the first one satisfies the condition, but the second component, we have 2 here and we have 3 there. We have 3 here and we have 2 here, and we have 4 here and we have 4 there, right? So only these two components satisfies the equality condition, but these two components do not satisfy them, all right? So A is not equal to A transpose. And if a matrix is not equal to its transpose, such a matrix is known as, anti-symmetric and it's called an anti-symmetric matrix. All right, another example, matrix B, 9, 10, 8, 5. All right, if I transpose B, this is equal to, I pick the row and change into a column, 9, 10, pick this row, change into the column, 8, 5. All right, now B is not the same as B transpose. Therefore, matrix B is said to be anti-symmetric matrix. Okay, so let's check a property here. If I have matrix A, B, C, D, all right, and I transpose it, this is going to give me AB becomes column AB, CD becomes column CD. If I pick the transpose form and I transpose it again, all right, let's see what we're going to get. Pick AC, we are transposing the transpose form. So we pick AC and then transpose it, becomes AC. Pick the BD, it becomes BD. So you notice that it has taken us back to the original matrix, right? Therefore, for any matrix at all, irrespective of the dimension, A transpose or transpose is always equal to A. Okay, that is one of the properties of the transpose of a matrix. If you double transpose a matrix, it takes you back to the original matrix. Now let's look at when we have a situation like A is equal to 0, 3, minus 3, 0. Okay, if I transpose A, this is going to give me 0, 3, pick this row, becomes a column, minus 3 and 0, right? Although A and A transpose are not the same, but if I find negative of A, okay, negative of A simply means multiply through A by negative 1. All right, so negative of A, I'm going to get 0 here, I'm going to get negative 3 here, I'm going to get positive 3 here, and I'm going to get 0 there. All right, now after applying negative on A, you notice that minus A and A transpose are the same because I have 0, negative 3, 3, 0, 0, negative 3, 3, 0. Okay, so if A transpose is the same as negative A, if A transpose is the same as negative A, then matrix A is said to be skew-symmetric. All right, but if still negative A and A transpose are not the same, then it's a definite antisymmetric matrix. Okay, let's look at another example. If I have matrix B giving us 0, minus 4, minus 6, 4, 0, minus 7, 6, 7, and 0. If I find B transpose, this is going to give me, pick the first row, becomes column, 4, minus 6, minus 4, minus 6. Pick the second row, becomes my column, 4, 0, minus 7. Pick the third row, becomes my column, 6, 7, and then 0. All right, now from here, B is not the same as B transpose because we have minus 4 here, but we have positive 4 here. So B is not the same as B transpose. But if I find negative of B, which means apply negative 1 on each and every component of matrix B, I'm going to get 0 here, negative 1 or negative 4 will be 4 here, get 6 here, get minus 4, 0, positive 7 here. Then I have minus 6, minus 7, and 0. Now if I compare minus B and B transpose, you notice that they are the same. So B is the same as B transpose, negative B. Since B transpose is the same as negative B, we said that matrix B is skew-symmetric matrix. All right. Now let's look at the third example. Say matrix C, which is equal to 0, 8, 12, minus 8, 0, 2, minus 12, minus 2, and 0 here. All right, so if we find C transpose, this is going to be, we pick the first row becomes the first column, 0, 8, 12. Pick the second row becomes the second column, minus 8, 0, 2. Pick the third row becomes the third column, minus 12, minus 2, and then 0. C and C transpose, although are not the same, but if we find negative C, simply means apply negative 1 on each and every component of matrix C. I'm going to get 0 here, minus 8, minus 12. I'll have 8, 0, minus 2. I'll have 12, 2, and then 0 there. All right, so we notice that C transpose is the same as negative C. If that is the case, then we say matrix C is known as skew-symmetric matrix. All right, so the only difference between a symmetric matrix is, one, if A is equal to A transpose, all right, then A is symmetric matrix. 2, if A is not equal to A transpose, then A is called anti-symmetric matrix. Antisymmetric matrix. All right, and then the third point is, if A transpose is the same as the negative of A, then the matrix A is known as skew-symmetric matrix. So these are the definitions of what a symmetric matrix is, what an antisymmetric matrix is, and what a skew-symmetric matrix is.